You know that incredibly frustrating feeling when a simple light switch in your house just gets stuck in the RN position?
Oh, yeah. You flip it, you push it. Maybe you even tap it with the handle of a screwdriver.
Exactly. But the light just stays glaringly, obnoxiously bright.
Right. But I mean, it's a mild annoyance in a hallway, sure.
Yeah.
But if we scale that down to a microscopic level to the inside of your own biology, it stops being a nuisance and, well, it starts being a catastrophe.
Which is exactly where we are heading today. Welcome to the deep dive. We've got a stack of your sources today, but the anchor for this conversation is a groundbreaking 2026 study from the journal Cancer Cell by Entrialgo Cadierno and colleagues.
Yeah, it's a fascinating paper.
It really is. Our mission today is looking at a broken, jammed-on switch inside a human cell. Because when this specific cellular switch gets stuck in the on-M position, it basically constantly shouts at the cell to divide and grow.
Right, which ultimately causes cancer.
Exactly. And not just any cancer, but cholangiocarcinoma, a notoriously stubborn type of bile duct cancer.
And, for anyone listening who might not be a medical professional, the reason this specific stack of research is so vital is that it gives us a front row seat to molecular warfare.
Yeah, it really does.
We're going to explore how scientists are finding entirely new ways to outsmart cancer, how the cancer immediately tries to build a detour, and how we can anticipate its next move. It's honestly a masterclass in biological problem solving.
So let's start with the battleground itself, cholangiocarcinoma, which we'll just call CCA from here on.
Makes it easier to say.
For sure. So this is a cancer of the bile ducts. Those are the tubes connecting your liver and gallbladder down to your small intestine. And looking at the global data, while it's considered rare, the incidence is actually creeping up worldwide.
Yeah, it makes up about 15% of all primary liver cancers right now.
Wow. And the standard of care doesn't seem to have a great track record, right?
It really doesn't. I mean, currently, the frontline treatment is just a combination of traditional chemotherapy and immunotherapy. But even with that combined approach, the median survival rate hovers around just 12.8 months.
That's incredibly tough.
It is. It's a highly aggressive, formidable disease.
Right.
And to understand why we struggle so much to treat it, we have to zoom way in on the molecular driver behind it.
Right. The engine of the cancer.
Exactly. In roughly a quarter of all CCA patients, the entire cancer is being driven by a mutated oncogene known as KRAS.
Okay, so KRAS is our broken light switch.
Essentially, yes. Think of the KRAS protein as like a relay station embedded just inside the outer membrane of a cell.
Just waiting for a signal.
Right. Its entire job is to listen for growth signals from the outside environment and pass that message down into the cell's nucleus.
Okay.
And in a normal, healthy cell, like the ones in your body right now, KRAS alternates between an inactive RFS state and an active on-end state.
So it toggles.
Exactly. When it's off, it's holding onto a low-energy molecule called GTP. But when a growth signal arrives, it drops the GTP, grabs a high-energy molecule called GTP, and turns on.
And then it just shouts, grow, to the cell.
Yeah, but just for a brief moment. And then a built-in timer forces it to turn back off.
So it's supposed to be a momentary pulse, just a quick flash of a signal.
Right. But mutations in the KRAS gene, specifically alterations that scientists label as G12D or G12V, they destroy that built-in timer.
Oh, wow. So it just can't turn off.
Exactly. The protein grabs the high-energy GTP, turns on, and then literally loses the physical ability to drop it. The switch is locked.
So it is just constantly flooding the cell with the instruction to multiply.
You got it.
But wait, I feel like I've read about KRAS drugs before. Didn't we have a massive breakthrough a few years ago? Drugs like sotorasib were everywhere in the medical news.
They were, yeah.
So if we have KRAS inhibitors, why are we still struggling with CCA?
It's a great point, but the devil is really in the structural biology here. Those first-generation KRAS inhibitors were a marvel, but they only targeted the OAF state.
Wait, what does that mean?
Well, they were designed to float around waiting for the KRAS protein to naturally cycle back to its GTP-bound inactive form. Once it did, the drug would bind to it and essentially cement it shut, so it couldn't wake back up.
Oh, I see. But if the mutation in CCA locks the switch in the on state, those old drugs are just sitting around in the cell waiting for a moment that never comes.
Exactly the problem. Furthermore, those older drugs were highly specific. They were engineered like a custom key to fit only one specific mutation shape, which is called G12C.
And let me guess, CCA doesn't have that shape.
Right. If we look at CCA patients, the G12C mutation is incredibly rare. It only shows up in about 1 to 7% of cases.
Wow.
Yeah. The vast majority of bile duct cancers are driven by different mutations, like G12D or G12V. So those older drugs physically cannot bind to them.
Which brings us to the new class of drugs tested in this 2026 study. They are called RAS on N multi-selective inhibitors.
Yeah, quite a mouthful.
Definitely. So the version used in the lab is RMC-7977, and the human version is daraxonrasib. From what I understand from the paper, instead of waiting for the switch to turn off to glue it down, this new drug goes straight for the live wire.
That's the paradigm shift here. This molecule is designed to recognize and bind to the KRAS protein while it is actively holding that high-energy GTP molecule.
Wow.
And because the active on-end state shares a very similar structural pocket across several different mutations, this new drug is multi-selective.
So it covers more bases.
Exactly. Doesn't care if your tumor has a G12D, a G12V, or a G12A mutation. If the switch is stuck on in, it finds it and neutralizes it.
So just a quick recap here. CCA is aggressive, KRAS is the broken switch locked in the on-end position, and our old drugs only worked on a rare mutation in the O-off-F position. Now we have a drug that targets the active on-end state across multiple mutations.
You summarized it perfectly.
So here's a question for you listening. If you were designing a drug, would you rather target a resting enemy or an actively attacking one? Because that's basically what this new drug does.
It's a great way to think about it.
But hang on, if you're taking a pill that shuts down this active growth pathway, what happens to your healthy cells? You mentioned earlier that healthy cells use this exact same KRAS relay station to divide naturally.
They do, yeah.
So wouldn't a drug that targets the on-end state just completely wreck the normal tissue regeneration in your body?
That was the massive hurdle for a long time, right?
Yeah.
And it's why research had to look at the in vitro lab data so closely.
Right.
When they put RMC-7977 into a dish with both healthy cells and human CCA cells, they found the drug was roughly 50 times more potent against the mutant cancer cells.
50 times? That's huge. How does the drug even know the difference?
It's all about the duration of the signal. Remember, a healthy cell only flips the KRAS switch on end for a tiny fraction of a second.
Oh, right. It pulses.
Exactly. Because the active state is so fleeting, the drug barely has time to bind before the cell naturally turns it off anyway.
Okay, that makes total sense.
But in the cancer cell, the switch is permanently on-end. The target is just sitting there 24/7. So the drug preferentially accumulates in the cancer cells simply because the binding window is permanently open.
That is so elegant. So the drug gets in, it binds to the live KRAS protein, and then what? The cell just, stops growing.
It does a lot more than stop growing. The researchers watched the drug successfully sever the canonical survival pathways.
Canonical just meaning the standard default wiring the cell uses.
Yes. Specifically, two communication lines known as the MMK arc and PI3K pathways. They are the primary cables connecting KRAS to the nucleus.
Okay.
When those cables are abruptly cut by the drug, the cancer cell experiences a catastrophic loss of survival signals.
So it panics.
Basically, it realizes something is fatally wrong, and it triggers apoptosis.
Apoptosis being programmed cell death. So rather than just bursting open like an infection, the cell neatly dismantles itself.
Right.
I saw in the sources they confirmed this by looking for something called cleaved caspase 3. What exactly is that?
I like to think of cleaved caspase 3 as the biological executioner inside a cell.
The executioner.
Yeah. Caspase are enzymes that normally just float around completely inactive. But when apoptosis is triggered, they get cleaved, meaning a piece is chopped off to activate them.
Oh, wait.
And once they're activated, they start systematically chopping up the cell's DNA and proteins. So when researchers see high levels of cleaved caspase 3 in the dish, they have proof positive that the cancer is actively self-destructing.
Okay, so the drug creates an absolute massacre in a petri dish. But a dish isn't a human.
No, it's not.
The researchers moved next to in vivo testing, taking human CCA tumors and implanting them into living mice. These are the PDX and CDX models.
Right.
And they saw the tumors either stop growing or shrink significantly. But there's a detail here that really caught my eye.
What's that?
To prove the drug was working, they didn't just measure the tumor size, they tracked a completely different gene called DUSP6.
Right.
Why go through the trouble of tracking a secondary gene? Why not just measure the drug levels and look at the tumor?
Because in pharmacology, you really need to prove mechanism, not just outcome. Getting a drug to physically enter a dense fibrotic tumor in a living animal is incredibly difficult. And even if a tumor shrinks over a few weeks, how do you prove it was your drug that did it and not just, a random biological fluctuation?
Oh, I see.
You need a real-time readout.
And DUSP6 provides that readout.
Yes. DUSP6 is a gene whose activity is directly driven by the KRAS pathway. If KRAS is screaming grow, the cell starts churning out massive amounts of the DUSP6 protein.
So it's like the immediate echo of the KRAS signal.
Exactly. When the researchers gave the mice the drug, they tracked the DUSP6 levels in the blood. And as the concentration of the drug went up, the expression of DUSP6 plummeted simultaneously.
Wow.
It's an undeniable cause and effect relationship, proving the drug was entering the tumor and shutting down the exact molecular target it was designed for.
It's like trying to figure out if the furnace inside a sealed factory has been turned off. You can't see the furnace, but if you watch the smoke stop billowing out of the chimney the moment you throw the power switch outside, you know you hit the right circuit.
That's a great way to visualize it. And that proof of mechanism is really what gave them the confidence to look at the human data.
So to recap the lab stuff real quick, the drug is 50 times more potent in cancer cells because the switch is always on. It triggers the cellular execution caspase 3, and they proved it worked in mice by tracking the DUSP6 smoke signal.
Perfect summary.
And for you listening, think about how hard it is to deliver a drug exactly where it needs to go. What stands out to you about tracking a secondary gene like DUSP6 just to prove the drug is working? It's pretty wild.
It is.
Which is where this story moves from fascinating biology to real human impact. The study highlights data from the phase 1 clinical trial of daraxonrasib, that's the human version of the drug.
Right.
There are 2 specific patient cases detailed in the sources that are honestly hard to read without getting a little emotional.
They are profound cases. I mean, take the first patient, detailed a 60-year-old woman with metastatic cholangiocarcinoma. Her specific tumor harbored a KRAS G12V mutation. She had already been through the brutal gauntlet of the standard of care. Chemotherapy and immunotherapy had both completely failed to stop her disease.
Which usually means you're out of options.
Historically, yes. But she enrolled in the trial and started taking daily oral daraxonrasib. And by her 7th cycle of treatment, scans confirmed her tumor had shrunk by nearly 40%.
That is incredible. And the most amazing part to me wasn't just the shrinkage, it was the durability. The paper noted that her response was still ongoing at cycle 32.
Yes.
That's well over a year later, still on the treatment without the cancer progressing.
And then we look at the second patient case. A 44-year-old man, but his tumor had a completely different mutation, KRAS G12A.
Okay, different shit.
Exactly. His disease was severe, with occult peritoneal metastases, meaning the cancer had aggressively spread into the lining of his abdominal cavity.
That sounds awful.
It is. But he achieved a 30% reduction in tumor size, and he gained over 10 months of progression-free survival.
I want to make sure I'm connecting the dots here. The reason these 2 cases are presented together is to highlight the multi-selective part of the drug's name, right? Patient 1 had a G12V mutation, patient 2 had a G12A.
You've hit the nail on the head. Prior to this drug, there were 0 targeted therapies for either of those specific mutations in CCA.
Wow.
The fact that one single drug reached into 2 different patients, recognized 2 different broken shapes of the KRAS protein, and shut them both down in real living human beings. I mean, it validates everything we just talked about regarding the lab data.
So bringing it all together, the human trials showed real shrinkage in patients with totally different KRAS mutations who were basically out of options.
Exactly.
So imagine being one of those patients. How does hearing about molecular multi-selective targeting change your view on the future of personalized medicine? Because I think it's just amazing.
It is truly life-changing.
But nature always finds a way, right? Especially when we're talking about cancer. If this drug is so effective, why did the mouse model show that after a month or 2, some of the tumors started growing back?
Yeah. This is where we have to acknowledge that cancer is an absolute master of evolution.
Right.
A tumor isn't just a static lump of bad tissue. It is a highly dynamic, adaptable engine. When you introduce a drug that blocks its primary survival pathway, it experiences massive evolutionary pressure.
So it fights back.
Yeah, most of the cells die. But a few survive by randomly mutating or rewiring their internal circuitry to build a detour around the drug blockade. The researchers call this oncogenic flux.
Oncogenic flux. They outlined 3 specific workarounds the cancer used, and the first one actually confused me a bit. They called it KRAS amplification.
Right.
The cancer realizes the KRAS proteins are being deactivated by the drug, so it just starts making extra copies of the KRAS gene to overwhelm the drug. Yeah. But the paper said it stores these extra copies on extra chromosomal DNA, or ICSI DNA. I remember from high school biology that human DNA is packed neatly into 46 chromosomes. How does a cell just have floating rogue DNA?
Well, it's a relatively recent and honestly terrifying discovery in oncology.
Yeah.
You're right, healthy cells keep their DNA strictly organized on chromosomes.
Yeah.
But cancer cells break the rules. When they are stressed by a drug, they can essentially chop out the specific gene they need, in this case, KRAS, and form it into a tiny independent circle of DNA that just floats freely in the nucleus.
Wait, so it's not bound by the normal rules of replication?
Not at all. Because it's detached from the main genome, an xDNA circle can copy itself uncontrollably.
Oh my
A
God.
single cancer cell might generate hundreds of these floating circles, each one churning out massive amounts of the mutated KRAS protein. The cancer simply produces more target proteins than there are drug molecules available to bind them. It wins by sheer brute force.
That is genuinely insidious. Okay, the second escape route they found was MYC overexpression. What is MYC?
So MYC is what we call a distal transcription factor. Distal, just meaning it operates far down the chain of command, deep inside the nucleus.
Okay.
It's essentially a middle manager. Usually KRAS sits at the cell surface and sends orders down to MYC. And MYC tells the DNA to divide.
So if the drug blocks KRAS at the surface, the cancer just bypasses it.
Yes. The cancer cell mutates to boost the MYC manager directly. MYC starts screaming at the cell to divide entirely on its own, completely ignoring the fact that the KRAS pathway above it has been shut down by our drug.
It cuts out the middleman entirely.
Exactly.
And then there's a third mechanism, SHP2 hyperactivation.
Right. So if MYC is the cancer finding a bypass below KRAS, SHP2 is the cancer trying to fix the problem from above.
Okay, how does that work?
SHP2 is a protein hub that sits upstream of KRAS. You can think of it as a funnel. It collects growth signals from dozens of different receptors on the outside of the cell and jams them all down into the KRAS pathway.
So it's forcing the issue.
Yeah. When the cell realizes KRAS is blocked, it hyperactivates that SHP2 funnel, trying to force the pathway back open through a sheer, overwhelming volume of upstream signals.
Man. With the tumor fighting back this hard, I saw the researchers tried adding immunotherapy to the mix.
They did, yeah.
The logic being, if the targeted drug is stressing the tumor, maybe the immune system can sweep in and finish the job. But it didn't work. Why couldn't the immune system see the vulnerable cancer?
This was a critical structural finding about CCA specifically. For your immune system's T cells to attack a diseased cell, that cell has to essentially present a biochemical ID badge.
Like an ID card.
Yeah. They use molecules called MHC class ion 2. Think of these as little display windows on the surface of the cell where it posts samples of its internal contents.
Like saying, hey, I've got mutated proteins in here, I'm cancerous, come destroy me.
Precisely. But the researchers discovered that these specific CCA tumors have a structural defect. They lack those MHC display windows entirely.
Yeah.
So even though the drug is doing its job and making the tumor vulnerable, the T cells just float right past. Without the display window, the cancer has a biological invisibility cloak.
So just a quick recap on the tumor's sneaky workarounds. It prints rogue DNA circles to outnumber the drug. It promotes middle managers like MYC to bypass the drug. It builds a massive funnel with SHP2, and it wears an invisibility cloak to hide from the immune system.
It is a brilliant, terrifying enemy.
So for you listening, if we connect this to the bigger picture, cancer isn't just a growing lump. It's a highly adaptable evolutionary engine. What would you do next to trap it? Because if you're listening to this, imagine the sheer complexity of what scientists are up against. How do you fight that?
Well, you anticipate it.
Yeah.
If you know exactly where the exits are, you can block them before the cancer even tries to use them.
Right.
This is where the study moves from observation into strategy, testing combination therapies.
They started by combining the new KRAS drug with standard chemotherapy gemcitabine and cisplatin. And in the mice, this completely outperformed either the chemo alone or the targeted drug alone. The tumors regressed profoundly.
It makes sense mechanistically. Chemotherapy is a blunt instrument. It damages the DNA and weakens the cancer cell's overall structural integrity.
Okay.
When you pair that structural weakening with a drug that cuts the cell's power supply, the cancer simply doesn't have the energy reserves required to build those evolutionary detours we just talked about.
But the strategy that really blew my mind was what we might call the double down approach. They took the new KRAS drug, RMC-7977, and combined it with an SHP2 inhibitor, a drug called RMC-4550.
Yes. Remember that upstream funnel SHP2 that the cancer uses to force the pathway open?
Right. It's like you're trying to stop a river from flooding a town. You build a massive state-of-the-art dam that's the KRAS inhibitor, but water always finds a way. It finds a weak point in the valley and creates a side channel, flowing right around your dam. So instead of just watching it happen, you take a pile of dynamite and you blow up the side channel at the exact same time you build the dam.
That is the exact pharmacology at play. By blocking the primary KRAS node and simultaneously plugging the SHP2 rescue funnel, they created a massive synergy.
Wow.
In the lab, this combination trapped the cancer and caused massive cell death. And when they put this combo into the living mouse models, it effectively doubled the time it took for the tumors to develop any kind of resistance.
And just as importantly, the sources noted they did this without causing massive overlapping toxicity to the animals. You're hitting two targets, but you aren't poisoning the whole system.
Which is really the holy grail of rational drug design. You aren't just throwing chemicals at a wall. You are using the tumor's own predictable escape routes against it.
So to recap the combos, pairing the drug with standard chemo starves the cancer's energy, and pairing it with a SHP2 inhibitor blows up the escape route. So for you listening, when tackling a complex problem in your own life or work, do you usually look for a single silver bullet or a combination of strategies to block all the failure points? Because this really reframes how we think about solving massive problems.
It does. It's never about finding one single silver bullet. It's about designing a web of strategies that anticipate the failure points.
Which brings us to the ultimate takeaway of this deep dive. This study isn't just a catalog of interesting lab results. It is a proof of concept that one of the deadliest, most untreatable forms of cancer is fundamentally addicted to this specific cellular signaling. For years, we literally could not reach the switch to turn it off.
But now with RAS(ON) multi-selective inhibitors, we can. And by pairing those drugs with therapies that block the backup generators, we finally have a viable translational roadmap for treating KRAS mutant CCA in humans.
I want to wrap up with something you hinted at earlier, this idea of anticipating the cancer.
Well, think about how oncology has operated for the last few decades. It has largely been a search for the perfect poison. We've been looking for a single drug, powerful enough to kill the cancer outright before it kills the patient. But studies like this reveal a different reality. Cancer evolves in real time. It uses tools like extrachromosomal DNA to outmaneuver our best single strikes.
So we can't just be soldiers looking for a bigger weapon.
Exactly. The future of treating cancer is about becoming better chess players. It's about looking at the board, anticipating that if we move here, the tumor will mutate there.
Wow.
And if we know its next move, we can set our pieces to put the cancer in checkmate before it even realizes it's trapped.
A molecular checkmate. That is a powerful thought to leave on. Next time you're frustrated by a stubborn mechanism in your life, whether it's a project at work or just a stuck light switch in the hallway, think about the scientists mapping the detours inside a single human cell. Thank you so much for joining us on this deep dive. Keep questioning, keep learning, and we'll catch you on the next one.